I mean, I've certainly gone over all these topics a number of times, so I mean, we could just take up each test, or I don't know. You know,
the course of the next 2 days.
Yeah. Yeah. I mean, yeah.
Does that mean MP completeness isn't going to be on the final?
Why do people ask dumb questions? No.
Like it wasn't on test 5.
I'm not even going to answer the question. If I don't teach it, I won't put it on the test. That was easy. Did you? All right.
I wrote a test back too long ago. You had new material in the test.
Fair enough. Well, I mean, one of the advantages of voting against covering incompleteness now is then it won't be on the test. All right, should we take up the tests? Should we do it on the board, or should we put up the answers on the screen?
No board.
No, let's do it on the board.
Do it on the board. All right, which test should we do first? The current one? It's fresh?
Yeah, let's work in reverse.
Work in reverse order. Now, seriously, guys, if you don't get it on the exam, you'll fail. All right? I'm not, you know, that's just it. You know, well, maybe that's not completely true. If everybody did as well as they did today, then I can't fail 2/3 of you. So 1/3 of you will have to be bailed out, right? But I can fail half of you without anybody caring. What am I doing? This is supposed to go the other way. I was supposed to be cleaning off the board. I've been marking for the last 2 days. You have to give me some. You know, actually, I think it's bad for me to mark them quick, because, you know, if I pout for a couple of days, and then I come back and see all your smiling faces, and then I'm in a better mood when I continue marking. I think that was a mistake. All right, so in this problem, we have a bunch of boxes, and each box has a weight and a capacity, and all right, so an instance is the capacity of the truck, and each box has a weight, a capacity, and a value, right? And the goal is here you have the truck, and it has some stuff in it already, and you want to stack the boxes. You want to say which subset of the boxes do I take, and what order do I take them so that no box breaks, and I maximize the sum of the values that I take, right? Surely everybody has the problem. All right, so the first question was to show that the greedy algorithm doesn't work. All right, now a couple of people during the test got confused about how in one question it says it works, and one question it says it doesn't work. All right, so in the one that it says it works, it says if I tell you a set of boxes and you need to take all of them, and it's possible to take all of them, then the greedy algorithm will tell you an ordering, right? But if you can't take them all because there's no ordering that works, then the greedy algorithm won't tell you which ones to take and which ones not to take. All right? So what do we want? We want an example where the optimal solution is bigger than the greedy solution, right? So the greedy solution is going to take the box with the biggest sum of the W plus C, right? So we want this number to be big, but we want it to be a bad box to take. Why is it a bad box to take? Well, because it has lousy capacity, right? Why does it have a big sum? Because it has a big weight, right? Now, we need to know what the optimal solution is, right? It has to be better than that. Well, to be better than that, it needs to have at least 2 boxes, right? Can we have only what happened if we only had a total of 2 boxes and we took them both? Is that possible that we have a total of 2 boxes? This box is up here? No, because if we took all the boxes, then the greedy algorithm works. Right? So we need 3 boxes. And what are the other 3 boxes? Well, we could have a weight equals 1 and a C equals 1 and a weight equals 1 and a C equals 1. Right? That's a perfectly good solution. Right? So we have, everybody see this? We have 3 boxes in the input. The greedy algorithm takes this one first, has a value of 1, but the optimal solution takes these 2. Right? So, more people got that right, but still half, probably half got it wrong. Any questions about that? All right, so the next question, lots of people got wrong. Lots and lots and lots. All right, so we have a truck, has a capacity of the truck. And what does that mean? That means it's the maximum you can put on top of this truck before either the truck breaks or the stuff breaks. Right? And we're adding a new box with a certain weight, a certain capacity, and a certain value. Well, let's first think about what can break, right? We could have the truck could break, the old stuff could break, or the new stuff could break. Actually, I didn't tell what the question is. The question is, we now call this the new truck, right? It's a truck with its stuff. And we want to know what's the capacity of this new truck, i.e., how much can we load on top before either the truck breaks or its stuff breaks, meaning its old stuff breaks or its new stuff breaks, right? So, what's the capacity of the actual truck, right? It used to be able to, these 2 are in fact the same. It used to be able to hold this, right? But we already put this on it, right? So this is how much more you can put on it before they break. But there's also the problem that the new stuff might break. And the new stuff, you can put this on it. Right? So what's our answer is the minimum of these 2. Right? Everybody good? All right, the next question. Oh, the next question, maybe it was a little, I thought about maybe putting in it as a hint, but then I stuck it in as a question. But whatever. The thing is, we have all these boxes, right? And there's 2 issues. The one is, what do you put on the truck? And the other is, what order do you put them on the truck? Now, if we're going to ask the bird a question, we would ask, we don't know which box to put first, right? We could ask, which box do we put first? And then there's, all right, let's try that here. Bird says, which box first? So how many answers are there? Okay, they're in answers, right? Depending on which box, right? She says, take box BK, right? Now, what do we give our friend? We need which boxes do you give? Right, 1 to n kind of minus k, right? And what capacity do you give? You give this capacity, whatever we just calculated there, right? The truck, but you put that box. If she says yes, right? Oh yeah, no, she did say yes. She said put that box on, right? So we put that box on. Everybody see that? And then what answer do I give? The friend gives me some answer, and what answer do I give? Same answer plus the box. All right? So that would be a fine bird friend answer. And I got a couple of those, even though I told you what the I try to be generous with that, right? But then we come to the next question, which is, what's the set of subinstances? Right? I don't know if I worded that wrong, but most people gave me, if I'm given the top instances, what were my friends given? Or my immediate friends. They didn't give me what my friends gave me. They didn't give me the whole set. So maybe I worded that wrong. But, right, so the problem here is, what is the whole set of subinstances that are going to happen? Right? We start off with the full set of boxes, and then we subtract off an arbitrary box. Right? And then we subtract off an arbitrary box. And then we subtract off an arbitrary box. What are you going to get here? You're going to get an arbitrary subset of boxes. Right? And how many are there? 2 to the n instances. Does that make sense? So this is bad, right? As soon as you do this, we're talking about 2 to the n subinstances, and the running time's too big, right? So, that's what makes this algorithm wrong. So if we could get a hint as to saying, if I knew which boxes to take, which box do I take first? Right? I take the box with the biggest. The greedy algorithm, remember the greedy algorithm sorts with respect to this. Right? So that one question was, the first thing we're going to do in our algorithm is we're going to sort with respect to, and so we're going to have to start writing the code, so we might as well write it here. Right? We've got stacking boxes. We have the input is C truck and the boxes. Oh, you want me to tell you another thing that, quite frankly, let me warn you right now for the exam. Something that always annoys me. You got to remember, I'm reading 50. One, I made up the questions, and 2, I'm reading 50 answers. Right? I don't want to read the question. Right? So don't repeat the question. Number of people read the question, then I get annoyed because I don't like reading it again. All right. So in here we're going to sort boxes by Wi plus Ci. Right? So now let's see the advantage of that is the first box now has the biggest thing there. So we asked the bird, should we take box B1 with the biggest Wi plus Ci? All right, we don't know, do we know the answer? No, we don't, because as we showed in the counterexample at the beginning, right, you don't necessarily take the one with the biggest sum. Right? So we don't know whether to take it or not. So if we had a bird to tell us, life would be good, but eventually we'll have to try them. But she's going to either say yes or no. Right? If she says yes, then we're taking this box with the biggest sum. So where in the ordering is it going to go? We don't know what future boxes we'll take. Right? Who knows what boxes is going to go in this truck yet? We now, because the bird told us this, we only have one box that's going to go in the truck. Right? And where in the ordering is it going to go? It's going to go first. Right? It's going to go on the bottom. So the joy of that is if she says yes, then we put it on the bottom. Right? So now what's the capacity of the new truck? Right? It's the minimum of C1 and C truck minus W1. Right? and we give friend C truck and the rest of the boxes. Right? And he gives us optimal solution. Optimal solution sub or something, right? Are people following this? And then what is our solution? Right? We add our box back in. Right? And our cost is his plus V1. People sort of follow that? If you had a bird, the bird told you to put this box with the heaviest, the biggest W plus C. We know it goes on the bottom, so we just go ahead and put it there. Right? And then we ask the friend, what to do with the rest of them. Right? Does that make sense? Now, if she says no, then we throw it away, in which case the friend gets this. Right? It's the same truck. And then our solution is the same as his. Right? Does that make sense?
Why are we taking the minimum of C1 and C truck?
Good. Well, that was question B, which said if we put B1 on the truck, how much more can we put on the truck? Well, we can't put more than C1 on the truck, or else B1 will break, right? And we can't put more than this on the truck because we already put this on and it had a previous capacity of this. So what we can put on the truck is the minimum of those two.
So why is it the maximum? Shouldn't that be the maximum?
No, because we can put on at most this and at most this. So we can put on at most the minimum of them. Right? Those is it min, is it max are kind of confusing, but you have to say to ourselves, well, is this going to make it, is it making it worse for us, better for us? Try an example. Figure out whether it should be min or max. Right? Everybody kind of good here? So then, our next question was, what is the set of sub-instances? In fact, I've made a number of changes to this question in case it ever gets used again to say, what's the entire set of sub-instances ever used by some friend, or what's the set of sub-instances we need to solve for dynamic programming, right? But basically, we start with C truck and 1 to N are the boxes, right? And what do we do when we cancel these out, right? So, and we make this smaller. Right? So a generic subinstance is going to be C prime bi plus 1 up to Bn, right? And where this is an arbitrary, well, this guy here is less than or equal to C truck, right? And this guy here is bigger or equal to 1. Right? And now then we set up a table. Right? The next thing is to set up a table. I didn't actually ask you the rewording of this is, what are you going to use to index this guy? Right? Well, I'm going to index it with C prime and I. Right? That's how I specify a problem. Does that make sense? So what I want to see up here is I want to see table 0 to C truck 1 to N plus 1 What do we got? Cost and bird answer, bird advice, right? Where we say solution C prime I is the solution, optimal solution to which of boxes BI to BN to put on truck with capacity C prime. Everybody understand what this problem is? You know, if you want, you can say, yeah, but we don't store this. We don't actually do this. We do its cost. Right? And then we sort the boxes. But in fact, maybe we should have done that before we set up the table, because that sort of redefines the sub-instance, but whatever. The base cases is now there's another tricky thing here that people didn't quite get, is which is the base case. So many people put down here cost 0 I equals 0 and cost C prime 0 equals 0. So does this make sense? Right? This says, what does this say? This said, if the truck has no capacity, then you can't put anything on it. So you're not going to get any boxes. Right? So does that make sense? No? Yes? Anybody say no? What about this guy? Does this make sense? Well, what is our instance? Let's say I is 0. Then our instance is B0 to Bn. Not only is it a big hard instance, but it has a box we don't even know about. What should we have here instead? What's the easy instance? So when we have no boxes, right? And when do we have no boxes? This is n plus 1. People kind of following that? No? All right. So this is partly, remember when we first did dynamic programming, we asked about the first edge to take. And the algorithm, the dynamic programming algorithm, turned it around so it looked like things were backwards. And we later said, don't do that. You know, ask about the last object, so when you turn things around, they look forwards, right? Well, here we asked about the first box. Why? Because it made our problem, our algorithm easier. Think about asking about the last box. You know, what are you going to stick boxes underneath? That would be weird, right? So we asked about the first box, but now our algorithm's backwards. And what does that mean for our algorithm to be backwards? It means that n plus 1 is our base case. Why is that? Because if I is n plus 1, then the boxes that we're considering are from n plus 1 to n, which is no boxes. Right? If I was n, we would be considering from box Bn to Bn, which would be box Bn. Right? And that would be pretty easy too. We could just put box, the box Bn fit, we put it on. But an easier instance is when it's n plus 1, because then you get no boxes. And that's when you get this. Right? Does that make sense? So you have to loop over this and loop over this and do that. All right? Then we want to loop over subinstances. Right? So what are our subinstances? They're these. You know, if you've already sort of done this already, it makes sense. So we loop over the values of C prime equaling 1 to C truck. So, and, right, so here we're getting the problem harder and harder, right, because we get more and more capacity. And we loop over I. What is I? What do we do here? How many people say we go 1 to n?
Into 1.
But remember our base case, we want to get the problem harder and harder, right? So we want to get more and more boxes. How do we get more and more boxes? Is we go this way. Right? In fact, what's our instance? That's kind of why in fact, I asked that in the question to try to warm people up to going forward, you know, doing this. Our instance is C truck 1. Right? So if we could solve 1 first, we'd be done and we'd go home. Right? So we're going to go backwards into 1. Right? And very few people got that. Almost everybody put 1 to n. Everybody kind of good that? Now what is our goal? Right? Our goal, in fact, let's put it over here. This here is our goal, is to solve this problem. Which didn't help me have a board to unraise. Everybody's good with this board?
So if we go from n to 1, isn't the very first problem we look at box n to n?
Sorry, what?
If you're going from n
Yeah.
to 1, right? So won't we be looking at box, the very last box?
Yes.
Then how will we get to the base case? Then we go to n minus 1 to n.
Well, we did the base case is when we have no boxes. Right? And then this case is when we have only box n. And then we do the case when we have box n minus 1 in n. And then we do the case when we have n minus 2 and n minus 1 in n. Right? They're growing, the list is growing backwards.
So what I don't get is we asked, did you say we're going to ask the what's the very first box? But what our break criteria was that, yeah, so should we take the first box? So, but now we're looking at the very last box.
Right, so that's true, but when we look at the last box, when we're trying to solve the problem with just box n, what we ask the bird is what do we put on the, do we put the last box, which is box, do we put the first box, which is box n, do we put it on the truck? Right? We'll get to that in a minute. So let's review the bird quest algorithm. Okay, here we loop over bird answers, right? So here's something what a lot of people did. If bird says yes, else. How do you feel about this? You should know, because if you said it, I scribbled on your page. Right? Now, we're not supposed to, we don't know what the bird said. Right? If we knew what the bird said, life would be really easy, but we don't. So we can't do if the bird says yes. We want to loop over the bird answers. Right? So really what we're doing is we're pretend bird says yes. And then we're going to pretend that she says no. Right? Does that make sense? We can't really, we could loop, but looping is kind of weird because we only have two things. Right? So loop here really means try them all. So she says yes, right? And what are we asking? Yes, put box BI on truck. That's what we asked her. We asked her, you know, our instance is this, right? So we asked her, do we put the first box on the truck, which is box BI? And she says, yes, put box BI on the truck. Right? So then we need a subinstance. What's our subinstance for our friend? We need to give him some C, right? And we need to give him which boxes? Right? We put box BI on the truck, so what boxes are left? BI plus 1 up to BN. Right? What capacity, what's this? This is what we computed when we put, right, so our truck had a capacity C. Was it C, C prime? What did we loop over? Was it C? Let's say we looped over C. Right? Our truck had capacity C, and we put box BI on, right? So here we'll set C prime to equal the minimum of Ci and C minus Wi. Alright, am I losing anybody?
Sorry, maybe I'm not getting the whole NQ thing, but if we do BI plus 1, if n is equal, I is equal to n, then is n plus 1?
Good question. If I equals n, then n plus 1 is saying that we have no boxes left. Right? If I equals n, then all I have is box n. If I put it on the truck, then my friend has no boxes. Right? And if my friend has no boxes, then who is my friend? It's the base case, which we solved already. Right? That's why we had the base case. Right.
But wouldn't it still be the same if you just picked it from the back and just suspended it in there or something?
Yeah. Yeah, you could take the last box and suspend it in thin air, but it gets a little, I mean, we would have to do something fancy, because you would have to make sure that these boxes don't break. You have to have an extra parameter. Who's above us? What's the weight below us? Right? There would be extra confusion. Right? So do people understand this here? So this is in sort of bird friend language. So we have to translate it over to dynamic programming language, right? We want to store cost yes, right? The cost of her saying yes. The cost of our optimal solution consistent with her saying yes. And what is that? Well, we ask the friend. The friend we ask cost. What's our C? Our C is this C prime here. And what's our, how many boxes? You know, we're starting with box I plus 1. Right? So this is the answer our friend gives. Does that make sense? Because we look, this is his subinstance. Where do we get his answer? We don't recurse. We don't have magic. We don't put English. We look it up in the table. Right? People good with that? And then, what's our solution? Ours has the extra, the value of the box, because we took it. Some people are looking stunned. Anybody who's looking stunned want to talk to me? Seriously, if you don't understand this, let me know. Does that mean everybody understands it? Should we quiz people on it? Don't be shy. I know you don't understand it, one of you. Right? Did you understand the sub-instance? What we're asking our friend? Do you understand how we translate it into looking it up in the table? Do you understand the key of the question that asks about sub-instances and their indexing, right? Because you need to know what are the sub-instances, you need to know how they're indexed so that you can then look them up in the table. Right? And then you take the answer from our friend and you add on the box that we just put on to get, what is this? This is the cost of the optimal solution to our problem consistent with the bird saying yes. Right? And then we pretend bird says no, and we have cost yes, oops, cost no equal cost. It's the original, is the capacity that we have so far, I plus 1. Right, does that make sense? Right, we don't change the capacity of the truck. And then we let k max equals best of, right, the argument best of cost yes and no, cost no. Right, so what is k? K is either yes or no. Right? Does that make sense? K, let k be yes or no, whichever one of these is best. And now we want to store it in the table. Right? Where do we store it in the table? Which problem are we working on? We're working on CI. Right? Our truck has capacity C. Our first box is I. And its cost K max. And our bird's advice right? Does that make sense? And then we do in loop I, in loop C. So we had this table, right? This is I equals 1 to n, and C equals 1 to C truck. And we're filling this table in. And our instance is this guy. And after we fill it in once, we have the bird's advice, so we can redo it and construct the solution. Anybody get that?
The I plus 1, can you explain it a little bit more? Why we're using I plus 1?
All right, because we put our boxes here. My problem is box I plus 1, box, oops, I start with box I plus 1, box I plus 2, up to box N. These are the boxes that I need to put on the truck. The bird tells me to put this on the truck. So this goes on the truck. What boxes do I have left? I have boxes I plus 1 up to N. How do I specify, how do I index this? How do I call the what do I call the sub-instance that goes from box I plus 1 to N? Right? I call it, I put it in the square, right, indexed by I plus 1. Right? Does that make sense?
Well, so that means initially your I is equals to N, right?
Initially what?
Your I is equals to N.
Yes! Yes! If you go back a few boards, we're doing loop I equal, first we did base case I equals N plus 1, And then we do I equals n minus 1, n minus 2 down to 1. And when we get to 1, when we get to I equals 1, then we're done. 3 minutes? All right. How are people doing? Could you do one of these?
So what do you mean by that? Like we put it down in the last square, like that is our instance. What does it mean by that?
What does that mean? That means what one of the first lines was loop over sub-instances, and we looped over C equals 1 to C truck and I equaling into 1, right? And now we're solving a particular instance. What's the particular instance we're solving? The truck has capacity C. We are considering boxes I to N. Right? That's the instance. You need to know when we're doing this, what instance are we solving? That's why on almost all of your papers, I wrote in big letters, what sub-instance are you solving? What are these sub-instances? Which one are you solving? Tell me what you're doing, because I don't know what you're doing. Right? More importantly, I don't think you know what you're doing. Right? So what you're doing is, I have capacity C on my truck, and I have boxes I to, right? You need to know what problem I'm solving. Does that make sense? So, let me tell you the most common answer to running time. All right, this is by far the most common answer. Most people said time equals number of sub-instances times the number of bird answers. Right? And then they would write down here 2n, which I didn't know what that meant. But what you would better is you say, hey, I have n sub-instances, I have 2 bird answers. Right? So my running time is 2n. So many people put that, and I would give you full marks if you did that, if what you did in your algorithm was you looped over I and you didn't loop over C, which is what most people did. Right? So that would be good. But then we want, what's the time complexity? And people would write, oh, it's 2 to the n. Right? Now, how did you get from this to this? All right, so that's wrong. Right? If this is the time, then that's the time. All right, so what's the actual answer? The number of sub-instances is C truck times n. Right? That's the size of this thing here. So our running time is 2 times C truck times n. Right? But the size of the input is the number of bits in C truck plus something times n, right? Because we have n boxes, right? Sort of times box size. So, but this is the thing that kills us here. So the running time is order 2 to the number of bits in C times n, right? And so it's exponential, not in the number of boxes, but it's exponential in the number of bits to write down the capacity of the truck, right? So if you just said exponential time, then I try to be consistent and give you 0 marks. But if you said exponential time, right? If you said exponential on n, then I would have liked to give you negative marks, but I didn't. If you said exponential in the number of bits in the capacity, then you're one of 3 or 4 people. All right, people, good here? And if you don't mind staying a few more minutes, we can do the last problem. All right, so now what we're going to cover, all right, we're going to now cover NP completeness. All right, everybody ready for NP completeness? we have two problems. We have the knapsack problem. And it's believed, right, we believe it has no quality time algorithm. Right? That's the state of the world. Right? If somebody tells you, give me a general algorithm which will give solve the knapsack problem in poly time, you tell your boss, hey, it's NP complete, we don't believe it's possible. Right? Then your boss says instead, hey, solve the box stack problem. And you might say, is it NP complete? Well, I don't know. It's probably not in the book. Right? Might not be in the NP complete book. But what we're going to prove is that this problem is at least as hard as this problem. Right? So what does that mean? It means if you could solve this, you could solve, oh, actually we're doing the NP complete reduction in the wrong way. Let me tell you something about NP complete reductions, is people always do them in the wrong way. Alright, so let's do this in the other direction. Let's pretend that we believe that this guy's NP complete. Right? For some reason you happen to know that this problem's NP complete, and you want to prove that this one is. Right? How do you do it? You say, well, if I had an algorithm for this, then I would have an algorithm for this. Right? So now am I getting it right? If I had an algorithm for this.
Yeah, because that's harder.
Yeah, if I had an algorithm
That's harder, yeah.
then I have an algorithm for this. But I don't have an algorithm. Oh no, we did have it right the first time.
Yes.
NP, right? But we don't have an algorithm for this. So we don't have an algorithm for this.
Is this why everyone gets it wrong?
Yeah, exactly. Exactly. Everybody gets it wrong because I do it at least once wrong. Right? Everybody, let's try this again. We believe there's no algorithm for this. Right? But we prove that if there was an algorithm for this guy, then
We have a program for this guy.
no, if we had an algorithm for this guy, we'd have an algorithm for this guy, but we don't have an algorithm for this guy, so we don't have an algorithm for this guy. Everybody get that? All right, so how do we do this reduction?
Yeah, yes.
Right? We're trying, we're pretending that we have an algorithm for this. We have an algorithm, right? And we want to solve this. So what we have is an instance to this. What's the instance to this? It's a volume of knapsack. And for each box, we have a volume of object, and we have a price of object. Right? This is what we want to solve. So, but we have an algorithm for this. So we map it over to an instance of this. The knapsack gets mapped to the capacity of the truck. Right? The value of an object gets mapped to the weight of the object. The price of the object gets mapped over to the value of the object. And the capacity of a box, well, we don't care how objects sit on top of each other, right? So we don't care what sits on top of a box. And then if you solve this, then the same answer solves that. There, we did NP completeness after all, so nobody can say you didn't get a lecture on NP completeness. So now it can be on the test.
No.
All right, so seriously, on Friday, come with all your questions because you will have to do these in a couple of weeks. All right? Seriously, you're going to have to do these. And I cannot imagine a dynamic programming question that's easier than the one that was on the test. Right? That's just that. Basically, it was the knapsack problem. Right? And some of you might say, well, I got confused about the sorting or the capacity of the truck. Yeah, but I didn't take off that many marks for that. Most people had the basic code wrong. Right? All right. See you on whatever day that is. Friday.